Yay!
Yay! All right. In the spirit of what we did before, we're going to use a previous result to get a new result. What we want, the last kind of object we're concerned with, is getting the moment of inertia of a hollow sphere. Now, here's the problem. If you try to attack this the way that we've done before, integrating over the surface of a sphere, it turns out that the integrals that you need to do are kind of long. They involve long trig substitutions, and it takes a long time to figure out. So my point is, let's be a little bit clever. Let's use this technique is used in physics pretty often. So this is one of my favorite ways I've seen this done. So we have a hollow sphere, right? In other words, we have something that's infinitesimally thin, but has a mass m and a radius r. So what do we know already? Last time we said for a solid sphere, the I was 2/5 mr squared, right? The way that we're going to attack this is we're going to say, how do you make a hollow sphere from a solid sphere? What if I added just a little bit of mass, a thin shell of mass to the outside of a solid sphere? In other words, what if you make it a little bit bigger? What if you increase the r a little bit? Here's the question I'm asking. How does the moment of inertia depend on r? So if I add a little bit more mass, if I increase the radius a little bit, the I is going to change, right? I mean, for sure there's that r squared there, but the mass has an r kind of buried inside as well, because if I make the solid sphere a little bit larger, the mass is going to get a little bit bigger, right? Because it's got a larger volume. So Rm, what is the mass? The mass is density times volume. Now the density is going to be the same. It's a constant everywhere inside, right? That's the idea, is that it's uniformly distributed. So this is going to be rho times 4/3 pi r cubed, right? So how I depends on r, really, if I add another thin shell to this thing, I is going to be 2/5. Where's my m? So this is going to be 2/5 times rho times 4/3 pi r cubed, and then I have my r squared. Okay, so let's kind of tighten this up a little bit. So this is going to be 8/15 rho pi r to the 5th. Okay, so that's really how I depends on r. So here's what I'm going to do. I'm going to do a little trick. Let's see if I add a little bit of r, if I have a slightly larger sphere, how does that change I? So in other words, in the language of calculus, how does I change with a little bit of r? Because that's what we're really doing. So what is di dr? So in fact, what I want to do is actually do a differential. So a little bit of I add a little bit of I if I change r a little bit. So this is going to be what I pull the 5 down. So this is going to be 5 times 8. So this is going to be like 8/3 rho pi r to the 4th times dr. So if I change dr a little bit, if I have a little bit bigger sphere, then I'm going to get a little bit more moment of inertia, right? And it goes like this. So that's the amount of that's the amount of moment of inertia that I've added by going to a slightly larger sphere. But that's if I subtract out, if I take away the sphere that was already there, this is the extra little bit of I get for a thin shell. This is what I want. So this is the I for a thin shell. That expression, that really is the I for the amount that I've expanded the sphere a little bit. So that means the I, this I that I'm interested in, is just going to be 1/3 rho. Okay, now I need to get that back in terms of M. So what I've got is, what is the mass of a spherical shell? Let's do it over here. The mass of a spherical shell is just going to be the density times the surface area of the spherical shell times its thickness dr. So that's going to be, what is the surface area of a sphere? Surface area of a sphere is 4 pi r squared times its thickness dr. Well, I've almost got all that stuff, right? I've got an 8/3 4 pi. I don't have the 4 pi, but I have the pi. So what I have is m over 4. If I cancel that out, I've got the pi, I've got the density, I've got r squared, so that's r squared. So this is going to be 8/3 m over 4 times r squared, and then I've got my dr up there. So, I mean, if you cancel those terms out, what you get is the moment of inertia of that shell. 2/3 m r squared. Look at that. That's pretty nifty. That's a cool little trick. We do this in physics, especially advanced physics, quite a bit, is just imagining, now what would happen if I changed a quantity a little bit, take its differential, and that differential is what we're really interested in, because what is a hollow sphere but a thin shell? So that's a neat little, a nifty derivation of the moment of inertia of a hollow sphere without having to do a really complicated integral. Cool.